Greetings and thank you for coming to my presentation. Everyone can hear me fine? Yes? Okay. So thank you. My presentation is on the mechanical testing of the 52M structural weld overlay. This work constitutes the final experimental tasks for my master's degree at The Ohio State University. And it follows two previous tasks, which I'll briefly go over here. But let me first start out by thanking our numerous sponsors: Arriva, Welding Services International, Babcock Wilcox Canada, Voestalpine, the Electric Power Research Institute, ESI, and Fronius for their technical and support of the project. So the introduction is, in the nuclear industry, in pressurized water reactors, there's a low alloy steel nozzle that's butt welded using filler metal 82 to some stainless piping on the other side here. And time has proven that the filler metal 82 is insufficient to prevent stress corrosion cracking in the weldment. What I just did is explain this diagram here. But first I'll go into the background of that, the motivation of the objectives, and the previous work that I just mentioned. And then I'll go into the various mechanical testing that we at Ohio State did on the mock-up overlay. And then we'll go into discussion, and hopefully we'll have time for questions at the end. So as I was saying, the filler metal 82 or 182 butt weld was insufficient to resist stress corrosion cracking in this weldment, which is very bad because this is primary water. It's never supposed to see the light of day again, and we want to keep it inside the pressurized vessel. So the chosen repair technique of the industry is to overlay structural weld overlay on top of this geometry that's a more developed alloy system of a higher chromium content to sort of halt this cracking propagation and provide an additional structural support to the surface of the weld. Well, the repair solution itself is not without its own problems. There have been numerous studies that have presented the solidification susceptibility of the filler metal 52M. And what this presents as is crack indications that are breaching the surface of the structural weld overlay. And these cracks have been associated with high dilution of the filler metal 52 or similar alloy with the cast stainless from the base metal. And this weld dilution has also been correlated with high power ratio with the hot and cold wire gas tungsten arc overlay process that they had been using to deposit this metal. So in an effort to solve the solidification problem to our structural weld overlay, we are investigating the CMT, the cold metal transfer process by Fronius, to provide a low input structural weld overlay deposition process. CMT it's a MIG-based, GMAW-based welding process that operates by mechanically reciprocating and simultaneously electronically pulsing the power characteristics of the arc, thereby drastically reducing the power input with respect to conventional processes, and even some other less conventional processes. CMT has lower power characteristics than in current and potential space than other processes. So I'll now go into some of the previous work. These first two slides are meant to compare the cold metal transfer weld fusion boundary. Here we see the 304L base metal being welded on top of with 52M, and there's a columnar and subsequent columnar dendritic regions that transition into weld metal composition fairly quickly. And in fact, in the previous study, we measured the transition region of this weld zone to be on the order of a few tens of micrometers, so around 20 micrometers wide. So past maybe a point right here, it's 90% filler metal all the way up to the top, which just goes to show that it is a process that can produce a low dilution overlay. And please also notice the scale bar. I'm going to compare it to another image real quick here. This is the typical GTAW overlay weld that we see. The microstructure is much coarser due to a lower heat cycle due to the higher heat input process. And also the planar growth region in this weld is just drastically larger than the one that we previously saw. And it should be noted that the average dilution of the filler metal bead above the fusion boundary is about 30%, 25 to 30%. So this isn't exactly 52M sitting on top of this 304. It's somewhere in between 304L and 52M composition. So the motivation of our work is to solve the hot cracking problem in structural weld overlays by altering the welding process from hot wire GTAW to cold metal transfer. And the objective of the study is to evaluate CMT's ability to fulfill the functional requirements of the structural weld overlay. Part one of the work entailed a design of experiment to optimize CMT welding parameters. We did a minimum design of experiment. We did two of them, which kind of defeats the purpose of a minimum. Of 21 welds each, we tracked the variables of dilution, toe angle, oxidation, which was sort of a derived property, heat input, and power ratio. And at the end, the factors of the CMT welding, the weave amplitude, the weave frequency, the travel speed, and the wire feed speed were optimized with 5 millimeters, 3.9 hertz, 10 millimeters per second, and 7.5 meters per minute. And the actual versus predicted measurements fell well within or close enough to the range that we accepted it as optimized weld parameters. Part two was using EDS to analyze the solidification features of the weld fusion boundary. And this is sort of an aggregated infographic of the findings of that study. It's best visualized using a pseudobinary phase diagram where we have 304L composition at 100% dilution on the left and 52% and 52M composition at 0 dilution on the right. What we're seeing in CMT welds is that as the planar solidification front progresses, it transitions through a cracking threshold region that was researched by EPRI to be between 40 and 62% dilution. So what we're seeing is a zone of a weld solidification morphology that doesn't exhibit the necessary solidification mechanism for cracking, passing our susceptible region, and afterwards the rest of the microstructure is free to solidify as it was designed to in nearly 52M composition. And we've even seen, So what we actually see in GTAW welds is that planar front breaks down almost in the middle of this cracking threshold region, which indicates the now microstructure that does exhibit the mechanism for cracking is also overlapping in a region that we know is solidification cracking susceptible. This isn't a coincidence. That's why the solidification cracking happens. And also the order of magnitude of these features is much different. As this metal solidifies from 100% base metal to about 28% filler metal, that happens over a course of maybe 10 micrometers, where the rest, the remaining 2.5 millimeters of deposition is almost 52M composition entirely. So after we did the DOE and after we did some EDS on weld samples, it was time to make a mock-up weld. We chose this particular heat of 52M with this composition, and we overlaid it on 8mm thick 304L base metal as a mock-up overlay, and we used this shielding gas, which was a combination of argon, helium, and CO2. The welding apparatus was the Fronius CMT advanced welding power supply hooked up to a 6-axis Motoman robotic arm. And the welding parameters were very similar to the optimized ones that I discussed previously, except we turned up the wire feed speed to increase our dilution a little bit to assuage some lack of fusion fears. The weld overlay mockup was designed from EPRI's requirements for a phase array ultrasonic test coupon, which was at the top 6 inches by 8 inches of overlay weld metal, and it was done with 5 layers to make a buildup of at least ½ inch. Phase array ultrasonic testing was performed at EPRI, and the overlay coupon was given two intentional defects to simulate cracks and flat bottom holes in both the axial and circumferential direction. And the phase array test was conducted in 5-degree increments from 0 to 80 degrees. After we made our nice overlay mock-up, we cut it up into samples that were intended for mechanical testing. Transverse side bending experiments were performed to test the strength of the fusion boundary and the weld metal itself. And also, tensile tests were performed to analyze the mechanical response of the weld metal alone. And those were performed at the parameters on screen. The results of the phase array UT test were pretty good. No unintentional defects were detected, and all intentional defects were detected. In addition to that, a prominent bead overlay signature was evident, which is not typical in GTW weld overlays and therefore not expected. So one concern in the report was raised that if a weld operator was running this coupon without prior knowledge of its fabrication, they might accidentally give a false positive to defects based on this grain structure that the technique revealed. The circumferential and axial notches were detected, as well as the flat bottom hole, which you can see highlighted in the brighter colors in the images. So I cut and pasted a little quote from ASME Section 9 for boiler and pressure vessel welding. So for corrosion-resistant overlay cladding, no discontinuity exceeding 1.5 millimeters in any direction shall be permitted, or any open discontinuity exceeding 3 millimeters shall be permitted. After side bend testing at 180 degrees for a total of 20% elongation at the surface, there were no open discontinuities whatsoever to be detected. Again, positive result. No defects detected. And tensile testing revealed that all the tensile specimens met and exceeded the ultimate tensile strength and percent elongation requirements for Section 9. We can see here that the special metals specification for the 52M is 30% elongation and 80 KSI tensile strength. And all 4 specimens here met and exceeded those goals, as well as the 304 base metal. The 52M also outperformed the base metal, which was also required by Section 9. Overlay macrostructures at the fusion boundary revealed no defects at the fusion boundary, no solidification cracks, which was the primary motive for this investigation, and also no lack of fusion, despite the CMT process being perhaps a misnomered cold process. It is It is a cold process with respect to pool, but we can see here that no lack of fusion defects because of that occurred. The microstructure of the overlays indicates a coarsening of the microstructure as the dendrites solidify upwards from the previous layers. And as each subsequent layer is laid on top of one another, the microstructure resets and just goes from small to large again, and then small to large again. A few defects were detected in this overlay in cross-section. This 113 micrometer long open discontinuity is possible lack of fusion at the toe region between layers. However, this is a defect that would be seen in even acceptable GTAW overlays, so it's not of paramount concern. It's also not detectable using current NDE techniques. Even with phase array, this might not be detected. Also, some similar defects, some possible lack of shrinkage or lack of fusion and shrinkage defects were detected in the weld metal itself. But again, these are pretty small defects with respect to some defects that are possible in the standard processes. So the conclusions are the results of the experiments. The phase array ultrasonic testing showed that mock-ups show no unintentional defects while also revealing intentional defects, which means that structural weld overlays made with CMT are inspectable with NDE methods with operator training, provided that they know what CMT does to a microstructure. And mechanical testing, side bend and tension tests showed that mock-up coupon was sufficiently strong and ductile to pass ASME Section 9 qualifications for weld overlays. I would like to thank John Lippold and Boyan Alexandrov for being on my advising committee, and the numerous contacts that we had with our sponsors, including Steve McCracken and Darren Barbarak, and the WJMG crew, and also you attendees. So thank you very much.